Hello, my name is Brandon Bishop, and today I'll be talking about nuclear thermal propulsion. Nuclear thermal propulsion is where you are taking a nuclear reactor into space and flowing a propellant through that. In today's case, when we're talking about that propellant, it will be hydrogen. We're flowing hydrogen through that nuclear reactor, and through nuclear fission, that propellant is getting heated up, and while it's getting heated up, it's gaining velocity and getting accelerated out of the back of the nozzle. That is different from your typical bipropellant, where bipropellant chemical rocket, where you are flowing both of the propellants into the combustion chamber with adding a source of ignition, and that is expelling that propellant out of the back of the nozzle. So here's our engine diagram of a nuclear propulsion rocket. You can see at the top we've got our turbo pumps. We're going to need a way to get the fuel from the fuel tanks into our rocket. So that's how with this design of NERVA, that's what they went with. As you can see, there's also two shields. You're still dealing with a nuclear device. You do not want whatever is in front of that device to get cooked with that radiation, whether that's the avionics on your stage, whether that's what's ever attached to the top of it, whether it's crew or if it's scientific equipment, you want that to be nice and safely shielded from your reactor core. Where, as you can see in the reactor core, it's your typical reactor. You're going to have some type of control rods and your nuclear material. With those control rods, you will be able to throttle that engine to some extent with how much nuclear fission is going on and change the velocity the exhaust gas is coming out at. As you look on the right, you can see a drawing of that reactor core. You can see that with those little holes, that's where you're going to flow the propellant through. While it goes through there, it's going to get hit with nuclear fission. That will add temperature and that will add velocity to that propellant, and you will get a higher specific impulse. In this case of NERVA, it was designed to be a second stage engine or a vacuum engine. They wanted that because they didn't want to fire this engine inside of Earth's atmosphere, dealing with pollutants and stuff. But going back to chemical, you can see with a liquid bipropellant engine, you're hitting that around 460 seconds of ISP mark. It's about the RL10's range. It's a really good rocket engine, and it's honestly really good specific impulse. Comparing that to a nuclear, on the other hand, we're getting all the way up to 860. We're almost getting to double of what a chemical can do. So that is nice to be able to achieve. With this, you can get a higher delta V from your rocket due to how heavy that ISP will be playing in the delta V equation. So yeah, it says 860, seen numbers in the 900s, so it's a very good way of producing propulsion. With that higher delta V, you're also going to get your quicker transit times. By this, you will be able to get to where you want to go faster, and you won't require the amount of gravity assist that you used on a chemical rocket engine. So this all started in the 50s, coming into the atomic age. The U.S. was trying to find what they could do with nuclear power, and they came up with the Rover program, which was to use nuclear power, nuclear decay, with a rocket engine. So that's where the early tests came up with the Kiwi engine, the Kiwi reactor, where they used uranium oxide plates. They flowed hydrogen over those, and it heated up the hydrogen and produced thrust out the back. In later tests, they did switch to a uranium dioxide design in that reactor. The initial reactors were showing wear, and they wanted to provide a stronger reactor, so they didn't have to worry about any problems that could come from a broken reactor. So while we have Kiwi here, if you look at it, it's kind of big. Got the name Kiwi because it's not meant to fly. It's named after the flightless bird kiwi, and that's kind of it. It's meant just to do ground testing. NERVA, on the other hand, look at the right here. This thing is meant to fly. You've got your where in a normal rocket you'd have a combustion chamber. This is where your reactor's at. You've got a pressure vessel that's containing that reactor in the inside, as you can see here. You've got your pressure vessel and then the reactors in the inside. Still got that shield because you don't want to hurt what's ever in front of that. But then as well as you can see that as the propellant goes through, it gets warmer and warmer and increases in velocity and comes out the nozzle. Fortunately, NERVA never got to fly due to non-engineering reasons. We'll leave it at that. But we do have a nice little clip here of it performing a static fire. So here we go.
At the Nuclear Rocket Development Station in Nevada, NASA, in cooperation with the Atomic Energy Commission, test-fired a powerful nuclear rocket reactor. The tests are part of an effort to develop nuclear-powered rockets for future deep space exploration.
So unfortunately, that is as far as NERVA got in flying. But if it would have flown, this is an application we could have seen with it, is using it and the space shuttle in conjunction to send spacecraft, send whether it's people, whether if it's scientific probes, further into our solar system. Shuttle would drop off the payload in low Earth orbit. The tug would come pick it up, dock with it, and send it to whether it's the moon, whether it's deep space, could be Mars, could be wherever. That's the benefit you gain of you having that extra specific impulse, that extra efficiency to your rocket engine. So we saw a boost back up. We saw a boost again in nuclear development in the 90s. This one was part of Reagan's Strategic Defense Initiative, where if you look at the image on the most right, you can see that there's these spherical objects. That's actually your uranium pellets. And by using pellets, you can increase your surface area, which your liquid hydrogen will flow through and thus heat up faster and produce a faster exit velocity, which will improve your thrust and your specific impulse. Fortunately, this didn't get too far into testing, but it's a design that could be used. So, 2025 and we still have not flown a nuclear engine yet. Well, that's hopefully changing soon with Draco. It is a collaboration between NASA and DARPA, which unfortunately with DARPA working on it, we don't hear too much about it, but we know they're working on it. It's something that's being looked into. And it's currently planned for a 2027 launch date. We'll see where that goes. But it's something to look forward to in the world of nuclear propulsion. So hopefully they can get that going and we can explore the solar system using nuclear propulsion. So, yeah, thank you.